that. Assignment 6, that's due next time on Wednesday. And final exam covering chapters 6 and 7 on Wednesday next week. Assignment 7 is up, and that will be due on Tuesday of next week. And I'll post assignment. Oh, that was from last week. I put that. So at the end of class last time, we were setting up this problem, but we didn't quite get to the end of it. So I posted the notes for it, but I'd like to go over it again real quick because your homework assignment on homework assignment number 6, the problem that uses the second principle of induction, is pretty much the same as that. Except instead of using implies and not, we're using and not, I think, or and not. Okay, so we want to prove that every propositional logic statement is equivalent to another propositional logic statement, which uses, well, which uses no connectors other than these. It doesn't have to use any connectors at all. So no connectors other than implies and not. So the proof is by the second principle of induction. Proof is by the second principle of induction on the number of connectors in such a statement. So the base case is n equal to 0 connectors. So let n be the number of logical connectors in a propositional logic statement. So the base case is n equal to 0. So a propositional logic statement with 0 connectors doesn't use connectors other than implies and nots. So there's nothing to prove. And now the induction step. So with the induction step, you assume that P0, P1, P2, all the way up to Pn, those are all true, and you want to prove Pn plus 1. So assume that any propositional logic statement with k connectors, where k is in 0 to n. Remember, in order to say the induction hypothesis properly, you must introduce a second variable other than the one you're doing induction on. So we're doing induction on n, but then to say the induction hypothesis correctly, we need another variable, k or l or whatever you might want to do. So any propositional logic statement with k connectors, k going from 0 to n, can be rewritten equivalently using no connectors other than implies and nots. Not assume. Show that. So that was our assumption. Now we want to show that a propositional logic statement with n plus 1 connectors does the same. N plus 1 connectors does the same. It's true for less than or equal to n connectors, but now we want to show it for n plus 1 connectors. Okay, well, say that P has n plus 1 connectors. The last connector in evaluating that statement is either, so let's add another sentence there. The last connector used to define P is either, well, it's or, and, implies, if and only if, or not. Therefore, either P is equal to A or B, P is equal to A and B, P is equal to A implies B, P is equal to A if and only if B, or P is equal to A not. Okay, because the last connector is one of those things. By the way, I'm not saying logical equivalence there. I'm not saying logically equivalent, I'm saying equals. Is that? Alright, so for example, like here, what am I talking about? Here, P would be equal to, say, like, X implies Y, or L and M, something like that. The last connector is the OR. There's other connectors inside here. Maybe, maybe not. Who knows? Okay, but the last one used is OR. So P is equal to A or B, A and B, A implies B, A if and only if B, or A not, where A has, capital A has little a connectors, capital B has little b connectors, period. Since P has n plus 1 connectors, A plus B is equal to n. Why not n plus 1? Why not n plus 1? How many connectors does P have? It has n plus 1 connectors. And then capital A has little a connectors inside of it, and capital B has little b connectors inside of it. So why isn't A plus B equal to n? Or n plus 1? Why is it equal to n?
Because the plus 1 is the last connector.
Yeah, this one right here. There's a or in this case. All right, there's one of them. All right, so here's A, here's B, A plus B is n, and then there's n plus 1. So, you isolate one of them and get rid of it, so to speak. All right, so in particular, since A plus B is n and A and B are non-negative, A plus A and B are both less than or equal to n. So A and B are both at most n, so A is logically equivalent to Q, where Q uses only implies and nots, or nothing at all. And B is logically equivalent to R. So why didn't I use equal here? Why is it logical equivalence? Right? Why is it logical equivalence? I mean, if it was L or M, for example, that's logically equivalent to L not implies M. Right? It's not equal to it, it's logically equivalent to it. They have the same truth value. They're not equal as statements. Right? So like A would be this, L or M, but we don't want ors, we just want implies and not. So I use implication tautology to get that. All right, so A is logically equivalent to Q, B is logically equivalent to R, and those use only ands and nots. So P, if it's equal to A and B, well, that's logically equivalent to Q and R. Q only uses implies and nots. R only uses implies and nots. So I would just like to turn this and into implies and nots. Well, Q and R is logically equivalent to Q naught or R naught not. Why? What did I use here? It's De Morgan's law. And then via the implication tautology, Q naught imply or R naught is the same as Q implies R naught. So this just uses implies and nots. Q's only got implies and nots inside of it. R's only got implies and nots inside of it, and everything else I've used to join up Q and R just implies and nots. Or P is equal to A or B, which is logically equivalent to Q or R, which is logically equivalent to Q not implies R. P is equal to A implies B, well, that's logically equivalent to Q implies R. Or P is equal to A if and only if B, well, that's logically equivalent to Q if and only if R, because A is equivalent to Q and B is equivalent to R. That's logically equivalent to this double implication, remember? Oh, I didn't finish that, did I? There's an and there. I don't want that and. Right, we want just implies and nots. That was an and. Q if and only if R is the same as Q implies R and R implies Q. And then doing the thing that we did before. This is Q implies R not, or R implies Q not. That's De Morgan. And then change that or into an implication. This is Q implies R implies Q not. That one took a little bit of finesse, but there it is. Or P is equal to A naught, where, A has little a connectors, but A is logically equivalent to Q, which only uses implies and nots. So in each case, whatever the last connector of P is, we've rewritten it using just implies and nots in a logically equivalent fashion. Okay, why doesn't the first principle work there? I mean, when you say A has little a connectors and B has little b number of connectors, it doesn't mean that little a is n. Doesn't mean that little b is n. I mean, n plus 1 could be equal to 7, say, in which case n is 6. Right? It doesn't mean that A is equal to 6. A could be 5, and B could be 1. A could be 6, B could be 0. A could be 3, B could be 3. It can be whatever, as long as it adds up to n. So the first principle is simply not enough. It doesn't imply the conclusion you're looking for. Again, the problems that use the second principle of induction are really more complicated than those that use the first. These examples I've given you so far, these are like a really good stock of them, although there's more. Maybe I'll post another one after class. It's a really good one. I think you'll like it. It takes a little while to explain, so I kind of don't really want to go over it because of time constraints, but I think I'll post something. All right, so the last homework problem for chapter 6. Where is it? Boom. Use the second principle of mathematical induction to prove that every propositional logic statement is logically equivalent to a propositional logic statement that uses no connectors other than ors and nots. Okay, so, I mean, more or less the same problem. Just not using the implies here, we're using the or. Fair enough? We can, fight through that problem, all right? I gave you the template for it here. All right. So other questions on chapter 6, assignment 6.
I guess I had a question on number 3, the
Okay.
inductive step.
Mm-hmm.
I was using the example that we did
Yeah.
with the unbound regions.
Well, all the regions, irrespective of bounded or unbounded.
Right. So I was at like the part where you drew the line, like the long line, and then you had all the different numbers, and then n-1 and n. I was not sure how I should draw that for number 3.
Well, that's just what I've got here.
Okay.
So when you add the last, so this picture I did it for n equal to 5 lines, but in general the picture will look the same as this one up here, right? So you're adding back in that last line h. This is a finite segment, well, finite length segment, finite length segment, finite length, finite length, finite length segments, until you get to the first one and the last one. There's n plus 1 segments here, not n plus 1, right? Because like this is segment 0, segment 1, 2, 3, all the way up to n. So that's n plus 1. The infinite segments, the infinite rays, are the first and the last segments. All right? Each segment takes a region before and cuts it into 2 regions. Okay? Well, a finite segment, if it creates a new region, it can't be an unbounded region. I'm sorry. A finite length segment can't take an unbounded region and cut it into 2 unbounded regions. A finite segment, let's go back to this picture. A finite segment will take a finite region and cut it into 2 finite regions. Or it will take an infinite region, an unbounded region, and cut it into a bounded and an unbounded region. Right? To cut an infinite, an unbounded region into 2 unbounded regions, you would need an infinite ray. I guess I need some more slope here. Okay, so yeah, like here would be something like that. Right? An infinite length ray cannot be on a bounded region at all. So it takes an unbounded region and cuts it into 2 unbounded regions. So, nor can it fit in a bounded region, right? You can't fit an infinite length ray in a bounded region. So it only goes in the unbounded regions. So when you're adding in that last line, the number of bounded regions created is the number of finite length line segments, which is what? So there's n plus 1 line segments. 2 of them are infinite length, so you disregard those. So there's n minus 1 finite length line segments. Each of the n minus 1 finite length line segments increases the number of finite length regions by 1. Does that help?
I think so. So if we drew that picture, would it be essentially just like that?
Yeah, just like that.
Okay.
Just with a little extra talk about bounded and unbounded regions and finite length line segments and infinite length line segments.
Okay. Also,
A little bit of explanation, that's all. Yeah.
with the base case, so you would need 3 lines to have a bounded region. So should we include?
Yeah, didn't I say that in the assignment?
I don't think you said it,
I
but
didn't say it, did I? Yeah, I guess you would have to do 3. But you can take the base case to be 3. It works for 2 as well, right? Because with 2, here this is 16 minus 12. No, sorry. With 2, 4 minus 6 plus 2 is 0.
I did it with one
With
line, like
one,
I
it still
showed,
works. 1 minus 3 plus 2, still 0.
right? So should we show both with one line and three lines, or should we
You
just
can do
do one
whichever
line?
base case you want. I'm not gonna be picky about that. You can take base case to be 1 line. You can take base case to be 2 lines or 3 lines. Doesn't matter. It
Would
works
it
either way. It's not interesting until you get to 3 lines anyway.
would it be wrong if you showed both one line and three lines?
Nah, that's fine.
Okay.
Yeah. Sometimes in proofs by induction, I haven't gone over any examples like this. I don't want to get into all the intricacies of it, but sometimes you have to do like several base cases. You can't do just like one base case. You have to do like several base cases.
Okay. Also on number two, the inductive step,
Mm-hmm.
you went over that before,
Mm-hmm.
and there was a part that I was kind of confused on.
Mm-hmm.
So you had on what you had written down, you had show that, and this is for the inductive step, show that n plus 1 squared is greater than 2n plus 5. Um,
Mm-hmm. Let me see.
I thought that that would be, I think it was on, yeah, the 16th, I'm pretty sure.
Yeah. So assume n squared is bigger than 2n plus 3. Some n bigger than or equal to 4. Show that n plus 1 squared is bigger than 2n plus 5. Show that that's true as well, right? When you replace n with n plus 1, you get 2n plus 2 plus 3, which is 2n plus 5.
Okay, I wasn't sure why it wouldn't be 2n plus 4, but
Well, n is multiplied by 2. So when
that
you
makes sense.
replace
I didn't
n,
distribute.
yeah, exactly. When you replace n by a two-term thing, you have to multiply 2 by by both terms.
Okay, that makes sense.
Yeah.
Thank you.
Mm-hmm. Alrighty. I apologize, guys. I have to excuse myself just for a minute. Oh, here it is. Okay. Any other questions on number 6, chapter 6? You can send questions or PDFs of your, drafts of your problems, by email as usual, and I will answer those as quickly as I can. All right. Excuse me. So, a final chapter. We're going to talk about. Excuse me. Metric spaces. The reason why I chose metric spaces is because they're not covered anywhere in the undergraduate curriculum. And it's an idea that should at least have heard of as a mathematics major. There, it's an axiomatic thing, which are nice definitions to work with. It's something, you just have a definition, just lists out a few axioms, and then you just work with those axioms. So I mean, it's good for developing a logical progression of things, and it'll help you. Most importantly, it'll help you get ready for the real variables 1 and 2, which is 4310, and you forget exactly. These are the two hardest courses in the undergraduate mathematics major. There's also the modern algebra, which is just slightly less hard, I think. But these are the real tricky ones, and this is a nice topic as an introduction to that. Okay, so a lot of the ideas that we're going to play around with here are things that go into your real variables course. So a metric space. So first of all, just for notation, let R bigger than or equal to 0 denote the set of non-negative real numbers. That is R bigger than 0 is equal to the set of all x in the real numbers such that x is bigger than or equal to 0. Okay, so definition. So a metric space is a set M along with what's known as a distance function. A distance function, sometimes called a metric. So a metric space, the distance function is sometimes just called a metric. A distance function d that measures distance between 2 points in the metric space, which satisfies 4 conditions. One, for all x in M, the distance from x to x is 0. 2, for all x and y in M, if x is not equal to y, then the distance from x to y is positive. So the distance between 2 points is always non-negative, right? But it's only 0 for, the distance of a point to itself. Okay, if the 2 points are different, the distance is positive. 3, the distance from x to y is the same as the distance from y to x. And for the distance from x to y plus the distance from y to z is bigger than or equal to the distance from x to z. And this last bit is called the triangle inequality. Okay, you must, so before I say anything else, you must, at this point, dispel all notions of what you think a metric space is. Okay, you're thinking to yourself, oh, you mean the real numbers, the triangle inequality. Oh, you mean the two-dimensional plane. Oh, you mean this. Oh, you mean that. No, I mean none of those things, and yet I mean all of those things. Okay, and more. A metric space is a set with a distance function satisfying these 4 properties. You may say nothing else about the metric space. You may not add elements of metric spaces. You may not subtract. You may not multiply. There is no algebraic structure to M. There is only a distance function with these four properties, and that's it. Okay, no other assumptions can you make unless it's a particular metric space. Okay, so this last bit is called the triangle inequality, and the reason why it's called the triangle inequality is because, I mean, you know, it looks like this. Here's x, and here's your point y, and here's your point z, and then this line segment is the distance from x to y. This line segment is the distance from y to z, and then this line segment is the distance from x to z. So that means the distance is the straight line distance between 2 points in the plane, right? Because of what I've drawn here. That's what that means. That's what that means. That the distance function is a straight line distance. No, it doesn't mean that. Not to torture you any further. It doesn't mean that. It's just that's one example of a metric space. Is when you have 2 points in the two-dimensional plane, and the distance between them is just a straight line distance. But of course, if you're using points in the two-dimensional plane, you can't just use one letter. You have to use a pair. Anyway, it should call to mind the idea of a triangle. Okay, examples of metric spaces. One, R, set of all real numbers in which the distance from x to y is equal to x minus y. So the real number line, here's your point x, here's your point y, and then this notion that you're all kind of familiar with of having 2 points on a ruler. The distance between them is just the difference between the 2 points algebraically. Not that you can add and subtract elements of metric spaces. In this metric space you can, because it's the space of real numbers. Okay, but not all metric spaces are the space of real numbers. Far from it. But that's the simplest example of a metric space. We will not actually prove that any of these things are metric spaces, but just throw out examples. I don't want to get into particular examples of metric spaces. I only want to show you what the different things, what different things it applies to. For all intents and purposes, all you will use is the 4 properties of the metric spaces and all of the consequences that you can derive from the 4 properties, which is a lot. Okay, even without any algebraic structure, without adding and subtracting and squaring and square roots and multiplying and dividing and limits and all that stuff. Okay, we're actually even able to do limits in a way that we'll get to. Not limits, but sequences. Limits of sequences. But we at least need to talk about it. All right. So R cross R, the two-dimensional plane, the xy plane, with the distance from 2 points xy to AB, right? Now in R cross R, points are pairs. So one must talk about the distance between 2 pairs. Right? I mean, you can use a single letter like P is a pair and Q is a pair and say the distance from P to Q is something, but we're going to refer to those pairs. And what is it? In the usual sense, well, it's the change in the x coordinate squared plus the change in the y coordinate squared. Right? That's the straight line metric. That's the standard Euclidean metric that that's based on the Pythagorean theorem and all that jazz that you've been talking about since whenever they do it in the school curriculum in Ohio. I'm not from Ohio, so I don't
The
know.
length of the vector, the
Yeah,
magnitude.
the length, the magnitude of the vector, all that, so all that stuff you're used to. But that's not the only way you can do a metric in R cross R. I mean, anybody from the actual city of Dayton? Is anyone actually, born? What is or Oakwood maybe? From Oakwood. I live in Beaver Creek, so Beaver Creek kids might
Up in Beaver Creek.
might not get it. So I mean, if you were in the city of Dayton or you were in any large pre-World War II development, um, and you want to know, well, what's the distance from my house to my friend's house? And suppose the terrain is fairly flat. How do you measure the distance? You don't measure the distance like this, unless you can fly. How do you measure the distance? From your house to your friend's house. So in pre-World War II housing developments and the homes that were built in the 20s and 30s, cities were planned on a grid, and you lived here and your buddy lives up over here, right? So what's the distance from here to there? Well, there's half a block, there's 1 block, 2 blocks, 3 blocks, 4 blocks,
Some of the
half block,
distances.
5 blocks, right? Yeah, I live 5 blocks away from Chris. All right, you're not going to measure it like that because yeah, we cut through our neighbors' yards, but we don't. All right, so in Beaver Creek things are a little more twisty turny. So this Beaver Creek is not, you know, wasn't developed until like the 50s at least. So here the distance is just the difference in the x coordinates plus the difference in the y coordinates. So instead of squaring, adding, and taking the square root, it's just this. And that's called the taxicab metric. This thing is called the Euclidean metric. After Euclid. This is called the taxicab metric after the idea of distance in a city. That's not the only way. There's infinitely many ways to do it, actually. I'm not going to cover all of them, but here's another way to do it. The distance from x to y is equal to the max. So, you've got these two numbers here, x minus a, y minus b. And that, it doesn't really have a name. It's called the real name is kind of weird, but the L infinity metric. We'll just call it the max metric. So these are all metric spaces using the set R cross R. So for example here, right, if we just take a couple points here, so we'll take the point 1, 0, and then the point 3, 5, right? The Euclidean distance is equal to the square root of 4 plus 25, which is square root 29, which is, I don't know what, 5, between 5 and 6, right? 5.5 or something like that. So that's the Euclidean distance. The taxicab distance, well, it's 2 plus 5. And the max metric distance is just 5. It's the larger of these two. You have those two numbers. You got the 2 and you got the 5. Which one's bigger? The 5. Okay, that's the max metric distance. Notice that the max metric distance is less than the Euclidean distance. The Euclidean distance is less than the taxicab distance. Okay, that's not a coincidence. That's true all the time. So in general, the max metric distance is less than or equal to the Euclidean distance is less than or equal to the taxicab distance. Each one is a metric space. Each one of these functions satisfies the 4 properties that the distance function in a metric space is supposed to satisfy. The distance from from a point to itself is 0. The distance between two different points is always positive. The distance from point A to point B is the same as the distance from point B to point A. And the triangle inequality, although it doesn't look like a triangle anymore, outside of these other things. All right, for 5, so I mean, things, you don't even have to be in the plane or 3-dimensional space or anything like this. So let S be the points on a 2D sphere. Well, this 3D sphere, like on the surface of on the surface. Sphere of some radius rho. So just some fixed radius rho sphere, like the Earth, right? Not really a sphere, but you can kind of think of it as such. How do you measure distance on a sphere? Does anyone know?
Would it be arc length?
Which arc length? Yes. Right. I mean, if you want to measure the distance between two points on the equator, you'd go along the equator, yeah? If you wanted to measure 2 points along the prime meridian, you'd go along the prime meridian, or any other meridian. I don't know what, not meridian, but longitude, yeah, I guess meridian. Longitudinal line, you just go straight north, straight south, right? So what does the equator and the longitudinal lines all have in common? They do what to the sphere? They cut it into
Hemispheres.
Yeah, 2 equal hemispheres, right? Any 2 points on a sphere, they're all joined by a unique, what's known as great circle. It is a circle that cuts the sphere into two equal hemispheres. So here's point X, here's point Y, and then the distance along a great circle is from here to here. So I mean, if you ever look at if you ever fly again, if any of the rest of us ever fly again, I'm sure some of you might. But like when you get on an airplane, you see the magazine with the airline routes on it, right? I mean, you have this flat rendering of the Earth. Of course, the Earth isn't. Well, sorry, don't mean to be controversial. Some of us assume the world to not be flat. Others of us would say that you're crazy. I don't know if anyone in here subscribes to that, but I mean, if you're of a mind that that we do live on a round sphere, or some approximation to a round sphere, and you look at the routes that the planes take, like here's Dayton or something, Here's, I don't know, Montreal. Right, you'll notice that the airplane goes like that. Right, the airline route is arced like that, and you think, well, why don't they go like that? Well, I mean, there's no straight line on a sphere, right? The route you're taking is a great circle distance, a great circle path. Excuse me. Well, typically, that's the shortest one. Not that you never deviate from that. Anyway, that's a metric space. Okay, I'm not going to prove it. We won't actually prove any of this stuff. But things get even weirder than that. Let f be equal to, or I guess we'll call it m. Let m be equal to the set of all f of x such that f of x is a continuous function on the interval from 0 to 1. So continuous function on the interval from 0 to 1. So here's 0, here's 1. So you just have some continuous function. Doesn't have to be positive. Just some continuous function. And then let the distance from f to g be equal to the integral from 0 to 1 fx minus gx. So absolute value of f minus g. That's a metric as well. That one we can actually prove is satisfies those four conditions because, it's just some basic just observations about integrals of positive functions. So lots of other examples of metric spaces. Some interesting, many of them interesting, some of them completely uninteresting. But they're all metric spaces. All right. An important concept in a metric space is the following. So given a metric space M, X in M, and some real number R bigger than 0, define the open ball of radius R centered at X is, so you write it like this, the ball of radius R around X, it's the set of all Y in M such that the distance from X to Y is less than R. Okay. So, for example, in the Euclidean, let me do the the taxicab metric first. In the taxicab metric, if you've got some point x, y at the center here, then this up here going to be like x, y plus r, x plus r, y, and then the same thing over here, x minus r, y, and then x, y minus r. This is the ball of radius r. So these should be open dots. That was wrong. That was wrong. So that's the ball of radius r around the point x, y. Remember, points are two-dimensional coordinates. They're ordered pairs. In the Euclidean metric, the ball of radius r around a point xy is, the disk. Which is bigger than this thing here. It's that. And then in the max metric, it's another square, just not this one. Let's see, let's fit this stuff. Oh, gosh, I lost that up. Anyway. In the max metric, the ball of radius r around a point x, y looks like this. So these different metrics give you just different notions of what a ball is in the two-dimensional plane. Each of them equally valid from the perspective of just being a metric space. Not definitely the Euclidean metric is kind of the most interesting of the bunch. Not that the others are without purpose. They are. So there's actually infinitely many metrics, and essentially what they are is sort of the balls are just sort of this bowing outward of things until you get to this square. But that's a topic for another course. So taxicab metric, Euclidean metric, max metric, these are the balls. So for next time, please attempt the following. Let M be a metric space. And x and y be an M with x not equal to y. Show that there are balls B are around x and B S around y such that, I guess I should say open balls. Open balls around x and y that are disjoint. Okay, so solve this for next time. Define R and S in terms of the distance from x to y. Okay, so R and S, they need to be stated in terms of that, the distance from x to y. All right, so for next time we'll do that. All right, guys, have a good day. Please email me with questions and concerns. I'll post solutions to the exams online, and yeah. All right. Okay. So we'll talk to you on Wednesday.